Welcome back. We've had our lunch. We're re-energized, ready to move on in lesson 9 to video 9H. Kim Shepard again, and we're still in regression. The main idea in this lesson, we're going to evaluate the quality of our linear regression equation. So, when fitting a linear regression equation to a data set, where the explanatory variable is x, the response variable is y, there are a few conditions on the data that we need to check before completing our analysis. So let's see what we should check. Number 1, the relationship must be linear. Why is this important? There are other models. You might look at your scatter plot and the relationship might not look linear. You might see more of a U-shape, like a quadratic relationship or an exponential relationship with a curve. But since we are building a linear model, fitting a linear equation to our data, it's important that the relationship look linear. So number 1, our relationship must be linear. So there are other models, but this is the one we're looking at. So even though there are other models besides linear that we could use, we're choosing a linear model, so in order to fit a linear model, your data have to look that way. Don't look linear, we're not fitting a linear model. Alright, so that's the first thing. The second thing, and if I've written too fast, you can always hit the pause button. The second thing, when we look at a scatter plot with the linear regression equation included, our data points should have equal spread about our regression line. So let's talk about what we mean by that and why that's important. So the data points must have equal spread about the point, or about the line. So just as an example, I'll put a little scatter plot over here. If this is your regression line, and here's your scatter plot, if the points are sort of scattered down here about this much, then as the x values get bigger, they should still be scattered about that same amount, roughly equal spread. Well, it won't be perfect, but roughly equal spread. What we don't want to see is that the points are not very scattered for small x values, and then as the x values get bigger, all of a sudden these points sort of really deviate a lot from our line. That's what we don't want to see. So we want roughly equal spread. The better picture was when the spread of those points with regard to the regression line was roughly the same. So one measure that we'll begin to look at is the standard deviation of the points about the line. And if it's not about the same, then we can't interpret its value correctly. So more on that in a minute. One measure we'll begin to look at is the standard deviation of points about the line. If it's not about approximately the same for all x values, then we can't interpret its value correctly. Okay, so equal spread. I tried to show you that with the scatter plot. Again, this is one we're going to come back to in a minute and talk about again. But we're going to look at the standard deviation of points about the line. We want that spread to be roughly the same for all x values. If it's not, we'll have difficulty interpreting that standard deviation. So that's number 2. Number 3. Again, pause if you need to. It's a wordy slide there. When looking at the scatter plot, there should not be any data points that are extremely separated from the main cluster of the points. Okay, and so why is that important? Why does that have to be true? So again, the scatter plot that I had up before, there weren't any points that were sort of crazy points away from the main clustering of other points. If you do have points like those, we need to be careful about those. They can have great influence on your regression line. They could be typos. They could be mistakes. If we had a point when you plotted your scatter plot, if you had a point like on this scatter plot that was way down here, all the points are here and you've got one way down here. Or if you had a point that was way up here by itself, you know, is that a typo? Were there really x values that big in the data set? Or was there really a point here for this x value that had this tiny little y value? So it could be that there are mistakes in your data. The other thing, if you have unusual points like this, that can start to sort of have some influence on your regression line. Your regression line might be pulled down by that. So when looking at our scatter plot, we want to make sure that there aren't any points like this that are separated from the main cluster of points. And again, if there are, we'll eventually discuss how do we handle points like that. So points away from the cluster of the regular points. Could be typos. One thing. Second thing, they might heavily influence that regression line. The other thing, they might not even belong to the population of data that you have. If this was a set of schools, and X has something to do with the size of the school, and then you throw in there like a giant online school or something, maybe it didn't even belong. So for now, how we'll handle those points, we'll identify them and we'll investigate, see if we can come up with a reason for those. So identify them and investigate them. And you know, obviously if they're a typo, we'd like to fix that, or if you are unable to fix it but know it's a typo, at least remove the point. If it really just is an unusual point, we'll talk about how you handle that too, or if it's not really in the population that you're studying, then that doesn't belong there either, then we would remove that point. Okay, with these three conditions, how do we check these three conditions? So to check that our data meet these requirements, we're going to carefully analyze two scatter plots. I've talked about the regular scatter plot that we've looked at previously, where the explanatory variable x is on the x-axis and the response variable is on the y-axis. So that's the first scatter plot, the one we're familiar with that we'll look at. And we're looking at that for the three things that we just went over. Does the data look linear? Is there equal spread about the line? And then third, the one we just looked at, are there any unusual data points? Oops. Unusual data points. So we're going to look at our regular scatter plot that we've traditionally looked at. We're going to try to answer that series of questions. In addition to the normal scatter plot that we're used to looking at, we're going to now look at a second scatter plot to check our conditions. So let's talk about this second scatter plot, something new. The second scatter plot is one where our explanatory variable still goes on the x-axis, but instead of plotting the x variable versus the y variable on the y-axis, on the y-axis, we're going to stick the residuals. So this time we've got the x variable is still on the x-axis, the explanatory variable, but we're going to look at x values versus their residuals. The name of this plot is called a residual plot. So as you can imagine, here on x, this is your regular explanatory variable. But now on y, instead of the response variable, the y-axis is going to be the values of the residuals. And again, it'll be a scatter plot, look a little different from the previous scatter plot. But we'll talk about the things that we're going to look for with the residual plot. So I think that's on the next slide. Okay, in a residual plot, we are graphing the x variable versus the residuals. What we hope to see is really like nothing. We'd like to see just a random scattering of points. The residuals, recall what they are. They're the errors. They're what's left over after the linear equation has been accounted for. If our choice of a linear equation was correct, then the residuals should look random. There should just be randomness left over. So now let's go on and talk about these three conditions again and how we'll see those show up in the residual plot. So in a residual plot, the first thing that we hope to see is random scatter. If that linear model really did a good job, then there shouldn't be anything interesting left over from that. And so we hope to see random scatter. We don't want to see a pattern to those residuals. Okay, remember, the residuals are required to have the same variation about the line for all the data we collected, and it's easier to see that on a residual plot than on the original scatter plot.
That's two.
I was going to say, I'm getting ahead of myself. Did I go over one?
You did one.
I did one. Oh, and I advanced that. Didn't even know it. Thank you. I was lost where I am. Number two. I knew something wasn't quite right. All right, number two, we hope to see equal spread in the data points as we move from the left to the right across the graph. Just like with the original scatter plot, we wanted to see equal spread. Now I'm caught up with everybody else. We want to see the same thing in that residual plot. But it's easier to see here. Essentially, this is going to be your explanatory variable. You'll see an example in the next video. Y is going to be the residuals. Think about those residuals. Some of those residuals might be 0, the points that were right on the regression line. Some of them are going to be positive, some of them are going to be negative. We'd like to see just a nice random scattering of points. We don't want to see a pattern. And however spread out the points are for small x values, we want them to have the same amount of spread for large x values. We don't all of a sudden want to see the spread of the points dramatically increase from what it was for smaller x values. So that's what this number 2 is saying. We want to see equal spread. Here I don't see equal spread. If I erase some points, now they're roughly equally spread. So that requirement's a little bit easier to see in the residual plot than it is in the regular scatter plot. All right, keep up with myself here. Number 3. A residual plot is also a nice place where we can see if we have any very large or very small residuals. You are looking for points near the very top or the bottom of your graph. If we have any of those, we'll investigate those. Remember what a large residual is. A large residual is just a point that really deviates, its observed value really deviates from its predicted value. If on your original scatter plot of x versus y, we had a point way up here, that point clearly has a very big positive residual. That might show up on your residual plot and be a point like way up there. Or if you had a point that had an extremely large negative residual, that might show up on your residual plot way down near the bottom of your graph. So this is number 3. When looking at the residual plot, not the original scatter plot, but the residual plot, we're again looking for unusual values. Points that have an unusually large positive residual or an unusually large negative residual. Okay, and if you stay tuned for the next video, we'll work out an example where we go through some of this stuff with a particular problem.